Welcome to Module 1, Section 2. In this session, we will discuss antimicrobial resistance, or in short, AMR, and how it spreads. At the end of this section, you should be able to define antibiotic resistance, discuss the drivers of antibiotic resistance, describe how antibiotic resistance and antibiotic residues spread through the environment. Let's start off by defining bacterial resistance. Bacterial resistance is when bacteria change over time and no longer respond to medicines, which making infections harder to treat and increasing the risk of disease spread, severe illness and death. Widespread inappropriate use of antibiotics is largely responsible for drug resistance. Thus, the incidence of resistance to a particular antibiotic is related to how and how much of the drug is used, as this drives selection of resistant bacteria. As mentioned in the previous slide, the widespread use of antibiotics is largely responsible for drug resistance. This slide shows findings of a study carried out in the USA, Europe, and Australia to find out the relationship between the total antibiotic use, measured in defined daily dose per 1,000 population per day, and prevalence of penicillin resistant forms of Streptococcus pneumonia. When the data was examined and the best fit lines drawn, three categories of countries around line 1, 2, and 3 emerged. The general conclusion is that there is a positive correlation between the quantity of antibiotics used and prevalence of penicillin-resistant Streptococcus pneumoniae. Countries such as the Netherlands and Denmark, with very low usage of penicillin, showed the lowest resistance rates. These findings show that reduction of antibiotic use or consumption is an important strategy in AMR prevention and control. The main drivers of antimicrobial resistance are outlined in this and following slides. They include misuse and overuse of antibiotics in humans, animals, crops, and environment, poor infection and disease prevention and control in healthcare facilities and farms, lack of awareness and knowledge on antibiotic resistance, absence of regulatory legislation, and lack of enforcement of legislation when available. Lack of access to clean water, sanitation, and hygiene, wash, for people and animals. Poor water, sanitation, and hygiene, wash, services leads to the spread of infectious diseases, which in turn leads to increased use of antibiotics. In addition, drug manufacturing facilities, animal and aquaculture farms, hospitals, and municipalities pollute water systems with antibiotic residues and resistant bacteria. Please note that many of the resistance genes observed in pathogenic bacteria likely originate from environmental bacteria. Antibiotics released into the environment further enrich for resistance genes. Furthermore, lack of access to quality, affordable medicines, vaccines, and diagnostics in human and animal health promotes antibiotic resistance. Vaccines protect people, communities, and animals by preventing infections and their onward transmission, whether antimicrobial resistant or not. For example, childhood vaccination against Haemophilus influenzae and Streptococcus pneumonia has reduced occurrence of these infections in children. Prevention of infections results in reduced use of antimicrobials for treatment, thereby reducing the selective pressures on microbial populations that drive the emergence of resistance. Lastly, the lack of academic curricula on AMR at educational institutions such as universities, colleges, and schools is a key driver of antibiotic resistance. Graduates leave college or schools without clear information on the drivers of antimicrobial resistance. These include human medicine and veterinary schools and colleges, agriculture, wildlife, water and environment, leadership and management, etc. In spite of the increasing threat of antimicrobial resistance, this graph shows that very few antibiotics have been developed in the last 20 years. The graph also shows that soon after the introduction of an antibiotic into clinical use, antibiotic resistance emerges. This trend causes global concern. Antibiotic residues are introduced in the environment in a number of ways. These include human health, therapeutic, and prophylactic use in human medicine, in health facilities, and in communities. Antibiotic residues are excreted by patients in urine and feces and eventually flow. In the environment, this could be rivers, lakes, soil. Animal husbandry, crop production, and aquaculture. For therapeutic and preventive use and growth production. Antibiotic residues are excreted by animals in urine and feces or flow from farms directly into the environment. This could be rivers, lakes, soil. Manufacturing firms, accidental and intentional release of antibiotics into the environment. The increase of antibiotics or antibiotic residues in the environment, which imposes widespread selective pressure on bacteria, leading to the selection of resistant strains. The resistant strains are also capable of transmission within the same species, for example, human to human, and among different species, for example, animal to human, and the environment, thereby creating the potential for the global movement of antibiotic resistance genes. As mentioned in the previous slide, antimicrobial resistant organisms are found in people, animals, food, plants, and the environment, that is, in water, soil, and air. Resistant bacteria spread throughout the environment in a number of ways. Person to person, infected people can spread resistant bacteria to others whether they have symptoms or not. This can happen through direct contact, indirect contact like coughing, or when someone leaves germs behind on a surface like a keyboard or doorknob. In hospital, when many sick people are close crowded together, it increases the risk of spreading healthcare associated infections between patients, healthcare workers, or caretakers. Animal to person, humans and animals can also pass resistant bacteria back and forth. Resistant bacteria are common in the guts and feces of livestock that receive antibiotics. Those bacteria can be transferred to people who are in close contact with those animals, such as farmers or veterinarians. Food to people, food contamination, including food of animal origin, resistant bacteria can also end up in food as a result of agricultural uses of antibiotics. Eating contaminated food may or may not cause symptoms, but the bacteria can spread to other people either way. Environment to people. Resistant bacteria in water, soil, and air may infect people directly or indirectly, for example, drinking resistant salmonella in water, or being injured by stick during gardening. The bacteria move from the soil to humans, or airborne diseases caused by resistant bugs.